Welcome to this explainer. Okay, let's just dive right into this. We're going to start by revealing a truth that honestly completely shatters how we see reality. The solid ground you're standing on right this second, it's not actually fixed, not at all. It's more like a living, breathing engine on this epic millions of years long journey. I mean, it sounds like pure science fiction, right? Just imagine if the ground beneath you was actively traveling thousands of kilometers. Because, well, it is. Our continents are absolutely not bolted down. Instead, they're floating on these massive, rigid slabs of rock, and they're moving just a few centimeters a year. And over deep time, that tiny, almost invisible crawl fundamentally shapes our entire world. Literally everything from the mountains we climb to the exact climate we experience.
Section 1. Wegener's Rejected Puzzle. The clues hidden in plain sight. To really get this, we've got to look at what is probably the ultimate scientific underdog story. So, picture this. It's 1912, and a German meteorologist named Alfred Wegener is just looking at an ordinary world atlas. And he notices that the continents seem to fit together remarkably well. I mean, almost exactly like pieces of a torn newspaper. But he didn't just stop at the coastline shapes. He put together this brilliant multidisciplinary case. Sure, he pointed out the perfect geometric fit of the Atlantic coastlines, but he also dug into the fossil record. Take the Mesosaurus, for example. It was just this small freshwater reptile. There is absolutely no physical way a creature like that could swim all the way across the massive, salty Atlantic Ocean. Yet, we find its identical fossils in both Brazil and South Africa. No way, right? He also found these heavy seeds of the ancient Glossopteris ferns scattered across 5 entirely different continents. Plus, he tracked ancient glacial scratches radiating out from a single central point at the South Pole, and even realized that the rock formations of the Appalachian Mountains perfectly match the Scottish Mountains when you piece the map together into a single supercontinent. A supercontinent he called Pangaea. Now you'd think with this overwhelming, perfectly assembled puzzle, people would listen. But actually, the scientific establishment harshly rejected Wegener's ideas. Just look at this quote from geologist Roland T. Chamberlain back in 1928. Wegener's hypothesis is not scientific, it is untenable. So why were they so incredibly dismissive? Well, it's because while Wegener clearly saw that the continents moved, he was missing the mechanism. He couldn't explain how. At the time, physicists calculated it was just utterly impossible for solid continents to plow their way through solid oceanic rock. And tragically, Wegener died on an expedition in Greenland in 1930, never getting to see his life's work vindicated. Section 2. The Missing Mechanism. Finding the smokeling gun. So the whole narrative shifts dramatically after World War II. Deep-sea sonar was originally developed for detecting submarines during the war, but it accidentally revealed something massive hiding at the bottom of the ocean. We're talking about a continuous 65,000-kilometer submarine mountain chain wrapping around the entire globe. And this wild discovery led to 2 massive lines of clinching proof in the 1960s. First up was paleomagnetism, or what scientists playfully call zebra stripes. See, as magma rises and cools at these underwater ridges, the magnetic minerals inside actually align with the Earth's current magnetic field. And because our planet's magnetic poles periodically flip, the ocean floor essentially records this symmetric, alternating pattern of normal and reverse polarity. It literally freezes Earth's history directly into the stone on either side of the ridge. Second, deep-sea drilling proved seafloor age gradients. The rock right at the ridge, brand new. But as you move farther away, the seafloor gets progressively older. This definitively proved that the ocean floor was constantly being created at the ridges and then recycled at deep-sea trenches. Finally, decades after his death, Wegener was vindicated. Section 3. Earth's tectonic engine. How the planet reshapes itself. And this right here brilliantly illustrates the huge paradigm shift of plate tectonics. The continents aren't just blindly plowing through the ocean floor, they are actually riding on top of giant interlocking lithospheric plates driven by immense subterranean forces. The absolutely crucial mechanism to understand here is called slab pull. Slab pull happens when a really dense, cold oceanic tectonic plate dips down into the Earth's hot mantle at a subduction zone. As it sinks into the depths, its enormous weight quite literally pulls the rest of the plate along behind it. Think of it kind of like a heavy tablecloth slowly sliding off a table, dragging all the plates and silverware on top of it along for the ride. Today, geophysicists consider this slab pull to be the dominant driving force of plate motion. It's even more powerful than the convective heat rising from the Earth's core. Now, when these immense plates interact, they do so at 3 distinct types of boundaries. Let's quickly break down these mechanical interactions. First, we have divergent boundaries. This is where plates pull apart, which creates new oceanic crust or deep rift valleys on land. Second, convergent boundaries. This is where plates violently collide. If an oceanic plate gets pushed down, crust is destroyed. But if two really buoyant continents crash into each other, neither one can sink deeply, so the crust simply buckles upward, building these towering mountain ranges like the Himalayas. Finally, transform boundaries. Here, plates are basically horizontally grinding past each other. They catch, they accumulate massive amounts of stress over time, and when they finally snap, boom, they trigger devastating earthquakes, like the ones we see along California's San Andreas Fault. So you might be wondering, how fast is all this actually happening? Well, let's look at some modern GPS satellite data. India is slamming into Asia at a blistering 5 centimeters per year, which, trust me, is huge in geological terms. Meanwhile, the Atlantic Ocean is slowly opening up at about 2.5 centimeters per year. And interestingly enough, that is roughly the exact same speed at which your fingernails grow. Over in the East African Rift, the divergence is a slightly slower 0.7 centimeters per year. And speaking of the East African Rift, this is arguably the most exciting place on the planet for geologists today. We are watching a continent splitting apart in real time. Stretching 3,500 kilometers, it's essentially a live laboratory where magma is welling up and physically tearing the African plate into two separate pieces. Millions of years from now, the Red Sea and Gulf of Aden are just going to flood right through this valley and they'll create a brand new ocean. Section 4. The supercontinent cycle, Earth's deep time. Okay, let's step back for a second to a much broader perspective so we can see an even grander rhythm. We're talking about a repeating process playing out over 300 to 500 million years, where continents slowly merge together into a single mass and then inevitably fracture apart all over again. Charting this immense chronological journey reveals something totally profound. Look at this timeline. 1.8 billion years ago, a supercontinent called Nuna or Columbia assembled. Then, by 1.1 billion years ago, we had Rodinia. Jump to 550 million years ago, and Gondwana united the southern land masses. And then 320 million years ago, Pangaea created a single global continent. So the really crucial takeaway here is that the famous Pangaea wasn't a one-time unique event. Not at all. It was just the most recent iteration of Earth's relentless, unstopping cycle.
Now, why does this matter to us today? Well, the far-reaching impact of this drift literally dictates almost everything on our planet. Mountain uplift, like the Himalayas, actually acts as a massive thermal engine driving the entire Asian monsoon system. When tectonic plates shift, they open or close oceanic gateways, which radically alters global ocean circulation. I mean, that's what brought on the deep freezing of Antarctica. The speed of seafloor spreading even dictates historical greenhouse climates by releasing varying amounts of volcanic carbon dioxide. And the breaking of land masses isolates animals, driving biological evolution. That's exactly how isolated species like Madagascar's lemurs evolved. Plus, and this is absolutely critical for our modern age, plate boundaries naturally concentrate the essential minerals we rely on today, like the copper and lithium heavily required for our electric vehicles.
Section 5. Our restless future. Where are we going?
So, if we know exactly where the continents have been and how fast they're moving today, we can actually extrapolate the map of the Earth into the deep future. Looking roughly 250 million years ahead, there are two leading models. In the first model, called Amaja, the unyielding forces of subduction completely erase the Pacific Ocean from existence. This would cause North America and Asia to violently collide. In the second model, Pangaea Proxima, the Atlantic Ocean eventually reverses its current spreading. It would ultimately close back up and unite the Americas with Africa and Europe once again. Either way, entire oceans are going to be wiped right off the face of the Earth. But what would living on this future supercontinent actually be like? Well, according to some cutting-edge 2023 research published in Nature Geoscience, it paints a rather grim picture. We're talking about a supercontinent engineered for a mass extinction. A massive, landlocked interior completely devoid of cooling coastlines, combined with intense volcanic carbon emissions and a naturally hotter sun, would cause temperatures to absolutely skyrocket. It could quite literally render the planet completely inhospitable for mammals. Which brings us to a deeply awe-inspiring thought to wrap up this explainer. The maps we study, the borders we build, the coastlines where we anchor our greatest cities, they are all remarkably temporary. We are living on a fleeting configuration of restless rock on a planet that operates on timescales we can barely even fathom. So I leave you with this final provocative question. What will be left of our human history when the Earth's internal engine inevitably rewrites the map once again? Thanks for joining this explainer, and as always, keep questioning the world around you.